Hello, welcome back to this series of lectures on numerical optimization. In the last few classes, we discussed about unconstrained optimization problems and some algorithms to solve those unconstrained optimization problems. Now, in practice, many problems are constraint optimization problems, and we need to solve those constraint optimization problems using suitable methods. For example, we have looked at this problem where we want to find out a box of minimum surface area which can accommodate certain volume. So, if we take a box let us assume that its length is L, breadth is B and the height is H. So, we are interested in finding the box of a minimum surface area which can accommodate a certain volume V. So, we can write this problem as minimize the surface area. Surface area is 2 into LB plus BH plus LH. Now, this is the surface area, and the constraint that we have is that it can accommodate, it should accommodate a certain volume V. So, LBH should be equal to some volume V, and the variables here, they are strictly positive quantities. So, we can say that L is greater than 0, B is greater than 0, H is greater than 0, and the optimization variables are L, B, H. So, you will see that finding a box of minimum surface area which can accommodate a certain volume V of a particular matter can be written as a constraint optimization problem. So, this is our objective function, and there are various constraints. The first constraint says that it should accommodate a volume V, and then the next three constraints say that all the quantities or all the variables here are strictly positive. None of them can become 0 or negative. Okay, let us look at some other problem. So, suppose we want to go from one place to another place. So, let us call these points as A and B. So, under the Euclidean norm, one can find a straight line path which minimizes the distance between the 2 points A and B. Now, suppose there is one constraint that we have to follow. Okay. So, we want to visit this road which is given here, a nonlinear road, and then go to the place B. Now, we want to find out a point, say P. Let us call this point as point P. Okay. So, our aim is to move from A to P and then P to B. So, what we want to do is that we want to find out the point P on this curve such that the total distance traveled, which is the distance AP plus distance PB, is minimized. So, let us assume that we are using Euclidean distance. So, let us denote this curve by say h of x equal to 0. So, what we are interested in is to solve the following problem, where we want to minimize the distance between AP plus distance between PB. Now, what are the constraints? The constraint is that the point P should belong to the curve Hx equal to 0. So, the constraint is that the point P should belong to this curve HB. So, we are interested in finding out the point P. I have not written this problem formally because we need to look at the coordinates of the point P and then write the objective function and the constraint appropriately. But what this problem formulation essentially means is that we are interested in that point P such that the distance between AP plus the distance between PB, that is minimized where the point P lies on the curve Hx equal to 0. So, like that in our daily life we come across lot of problems which are constraint optimization problems. And it is important to study the behavior of these problems and develop some efficient algorithms to solve such problems. Now, many times these constraint optimization problems can be written as unconstrained optimization problems and then solved. And therefore, it was important to study unconstrained optimization problem, unconstrained optimization theory earlier, so that we are in a position to study the constraint optimization theory. Now, general constraint optimization problem would look like this. So, minimize f of x subject to x belongs to x. Now, as usual, this f is an objective function and this x, this is called feasible set, or this is also called constraint set. So, this is a typical constraint optimization problem. So, when this x is the n dimensional space of real numbers, then when the capital X is n dimensional space of real numbers, then this problem becomes unconstrained problem. Now, some of the typical constraint optimization problems that one comes across are the following. So, one problem is that if you want to minimize C transpose x subject to the constraint Ax equal to B, x greater than or equal to 0, where A is a m by n matrix and without loss of generality we assume that rank of A is equal to m. So, C is a n dimensional vector, B is a m dimensional vector and x is non-negative. So, the objective function is to minimize C transpose x subject to the constraint that x equal to B, x greater than or equal to 0. This is commonly known as a linear programming problem, because the objective function is linear in the variable, the constraints are linear in the variables. So, this is a linear programming problem. So, later on we will see how to solve these kinds of problems, because they are a very important part of optimization problems and there exist very good methods to solve them. So, in this course sometime later we will study how to solve these kinds of problems. So, this is called a linear programming problem. Again you will see that this is a constraint optimization problem. Let us look at another example. Minimize half of x transpose Hx plus C transpose x subject to Ax less than or equal to B, x greater than or equal to 0, where H is symmetric and positive definite matrix. And let us assume that A is m by n matrix and rank of A is equal to m. So, the objective function here is a quadratic function, the constraints are linear. So, many problems in practice can be posed as problems where the objective function is quadratic and the constraints are linear in the variable. So, here the variable is x and we want to solve this kind of problem. So, this set of constraints x less than or equal to b and x greater than or equal to 0, in this case they form the constraint set, so which we have called it as capital X. So, this is our constraint set. So, you will see that lots of problems that we come across in practice are constraint optimization problems, and therefore, it is important to study the nature of solution of these constraint optimization problems as well as some algorithms to solve these constraint optimization problems. So, in the next few lectures, we are going to concentrate more on the constraint optimization problems, the nature of the solution, how does one get the solution. Now, if we recall, in the unconstrained problem case, where we solve this problem, we saw that the necessary condition for x star to be a local mean is that the gradient of f at x star is 0. We assume that f is smooth. So, what I mean by smooth is that second derivative exists and it is continuous at every x in the domain. So, the necessary conditions for the local minimum of this problem are that the gradient of this function should be 0, and the sufficient condition is that the Hessian matrix should be positive semi-definite. Now, if the Hessian matrix is positive definite, then we say that at that point x star where the Hessian matrix is positive definite and where the gradient of the function vanishes, we say that that point is a strict local minimum. Now, we are looking at a different problem where we want to minimize f of x subject to x belongs to x. Now, what kinds of optimality conditions exist for this problem? So, remember that here we said that the gradient of the function should vanish. Now, that condition alone may not be enough for this, because now we are working with some constraint, and can we arrive at a condition which is somewhat similar to the first order necessary condition for a unconstrained optimization problem, and how do we make use of this set x in order to write that optimization condition for a constraint problem like this, and that is the part of the next few lectures. Okay, so as I said that constraint optimization are very important, and let us start looking at a general constraint optimization problem. Now, a typical constraint optimization problem looks like this, where we want to minimize the objective function f of x subject to some constraints of the type h j x less than or equal to 0. So, these are the inequality constraints. Then there could be some equality constraints, EIX equal to 0. So, there are L inequality constraints, M equality constraints, and further x belongs to some set S. So, all these together they form the constraint set or the feasible set of this problem. Sometimes it is also called the feasible region. So, the inequality constraints in this course we are going to denote it by Hj, and all Hj's are functions from Rn to R, and all equality constraints we are going to denote by Ei, where Ei again is a function from Rn to R. Now, we will assume that this f, Hj's and Ei's are all smooth. So, what I mean by smoothness is that they are their second derivatives are continuous at every point in the domain. The second derivatives exist and they are continuous at every point in the domain. So, we will make this assumption throughout, so that it is easy to write down the optimality conditions in terms of the derivatives at a later point of time. Now, the feasible set X is basically the set of points in the set S which satisfy the constraints Hjx less than or equal to 0 and Eix equal to 0 for all j is going from 1 to L and I is going from 1 to M. So, this is going to be the feasible set of our constraint optimization problem. In many problems, this S is nothing but Rn, and therefore, we can replace S by Rn here and simply write it as x is equal to all x belonging to Rn such that Hx less than or equal to 0 and Ex equal to 0. So, our problem is to minimize f of x subject to x belongs to x. So, this is a compact way of describing the constraint optimization problem which we are looking at. Now, let us assume that x is non-empty set in Rn. Because if x is empty, then we really cannot solve this problem. And suppose x is singleton, then that point, the singleton point in the set x will be an optimal point. So, let us assume that not only that x is non-empty, but x is also not singleton. Now, similar to the unconstrained optimization problems, we have to see the notion of local and global minima in the context of constrained optimization problems. So, remember that we are trying to solve the problem minimize f x subject to x belongs to the capital set X or x belongs to the feasible region. So, a point x star in the feasible region is said to be a global minimum point of f over x if the value of f x is greater than or equal to f of x star for all x in the feasible region. And if this inequality holds strictly, then the point x star is called a strict local minimum. So, that is if f of x is greater than f of x star for all x in x, where x is not equal to x star, then x star is said to be a strict global minimum point of f over x. Now, as is the case of unconstrained optimization problems, these global minima are hard to obtain. So, one looks at the local minima. So, one can define the local minima in the following way. So, a point x star which is feasible is said to be a local minimum point if there exists a neighborhood of x star or there exists a epsilon neighborhood of x star such that f of x is greater than or equal to f of x star for all x in the epsilon neighborhood. And again, when this inequality is strict, we called it as a strict local minimum. Now, let us see some examples of the local minima and the global minima. So, let us consider a problem where this is x, suppose this is the origin, and so on the y axis we will plot x. So, this is f of x, this is our origin, and suppose that the function that we have is in the interval say a to b, and the function is like this. So, although the function may be defined over the entire real line, we are only interested in the closed interval a b. So, what we are interested in is solving this problem, minimize f of x subject to x belongs to a b. Now let us look at the global minimum first. Now, if you just concentrate on this part of the function, this part of the domain a b of the function. So, we are not interested really in this part, what happens beyond the other points, I mean beyond the closed interval a b. So, if you look at the definition of the global minimum, it says that f of x star should be less than or equal to f of x for all x in the constraint set or the feasible set, and remember that x star also should belong to the constraint set. So, by that definition, this point becomes a global minimum. So, in the constraint set, there is no other x which has a value, function value which is lesser than this. So, this is a global minimum. Now, if we look at the definition of a local minimum, you will see that those are the points where in the epsilon neighborhood of those points, if you look at all the feasible points in the neighborhood, the function value is at least the function value at the given point. So, for example, so this point is also a local minimum. Now, if you look at this point x equal to a, you will see that in the neighborhood the function value is increasing. So, this is also a local minimum. And if you look at this point, so in the neighborhood you will see that the function value does not increase, or in the neighborhood the function value does not decrease. So, this also is a candidate for a local minimum. So, the function value is at least the value at this point. So, this point is a local minimum. So, there are three local minima for this one is x equal to a, then this point and this point. These are the 3 local minima, because in the neighborhood the function does not decrease. There exists at least some epsilon neighborhood around these points where the function value does not decrease. So, these are the local minima. Now, this point is also a global minimum with respect to the constraint set A B. Now, if you look at these 2 points, here the function value locally does not decrease, but does not increase either, it remains constant. So, this is a weak local minimum. So, the corresponding point So this point is also a weak local minimum. So, where the function value does not increase or decrease, but remains constant in the epsilon neighborhood. So, these are different characteristics of the local or the global minima. Now, as is the case in case of any optimization problem, we are interested in finding the global minimum of a given optimization problem, but that is difficult to find because of the same reasons that we discussed for an unconstrained problem. So, we will be interested in looking at the local minima, their characterizations, and how do we design efficient algorithms to find out the global minima. Now, you will also notice that the first order necessary conditions that we discussed for an unconstrained optimization problem may not always hold at local minima. So, at this point the gradient of the function vanishes. So, this is fine, this point is also fine, but if you look at this local minimum, if you take the one directional derivative of the function at this point, it is not 0. So, you will see that the first order conditions that we studied for unconstrained optimization problem cannot be directly used to characterize the local minima of a constrained optimization problem. So, we need some extra conditions to characterize the local minima of constrained optimization problems. Okay. Now, under suitable conditions, the first order necessary conditions for constrained optimization problems are also sufficient, and those problems are called convex programming problems. Now, in the unconstrained case, we saw that if you want to minimize a convex function over the set Rn, then the first order necessary conditions are also sufficient. Now, similar result holds in the case of convex programming problem, where we are writing a general constrained optimization problem, but then the functions which are mentioned here, the objective function as well as the constraints, they have certain characteristics, and because of which these problems are called convex programming problems. So, the objective function f(x) is a convex function. So, the objective function that we want to minimize is a convex function. The EIx equal to 0 is a affine constraint. That means, EIX is of the form AI transpose x plus BI for all i's going from 1 to m. So, all the equality constraints are of the type AI transpose x plus BI equal to 0, or they are affine constraints. Then the Hjx less than or equal to 0 constraint, the inequality constraint is such that the function Hjx is a convex function, and further S is a convex set. So, now if you look at these constraints, so Hjx less than or equal to 0, where Hjx is a convex function. So, we have L such constraints. So, in intersection of these, so Hjx, the set of all x such that h1x less than or equal to 0, where h1x is a convex function, is a convex set. Now, we have L such constraints. So, the intersection of all convex sets is a convex set. Then the intersection of that with a affine set is also a convex set, and the intersection of this convex set with another convex set is a convex set. So, we have studied this property of convex sets earlier, that the intersection of any collection of convex sets is a convex set. So, the constraint set is a convex set, the objective function to be minimized is a convex function, and such problems are called convex programming problems. Sometimes when one wants to maximize a concave function, that problem also subject to a convex set, that problem also can be written as minimization of a convex function, because maximization of a concave function is same as minimization of the corresponding convex function. So, such problems are called convex programming problems, and for such problems every local minimum is a global minimum, and there are no the set of global minima form a convex set. So, if you want to minimize a convex function, now you will see that suppose we want to minimize it with respect to the set AB. So, you will see that this is a, so this point is a global minimum. And if you look at another convex function, so let us look at another convex function. And we want to minimize it with respect to the set AB. Now, you will see that all these are so this entire set of points they are global minima. So, you will see that they form a convex set. So, not only that the there is no question of local minima in the convex programming problem. In fact, all the global minima which are possible, they form a convex set. So, this is an important property of convex programming problems, and further, as later on we will see that the first order necessary conditions for a convex programming problem are sufficient under certain conditions. So, we will look at those things sometime later. So, these are some important properties of convex programming problems, and later on we will see these problems in detail. Now, let us look at the problem minimize f x subject to x belongs to x, which is a compact form of a constraint optimization problem where x is a feasible set. Now, there are different ways of solving this problem, and one of the ways is to convert it to an unconstrained problem or reformulation to an unconstrained problem. So, let us look at some ways of doing that. So, suppose that we have to solve the following problem, minimize f of x1 x2 subject to the constraint that x1 greater than or equal to 0. Now, here there are constraints on the variable x1. So, what one can do is that since x1 is going to be non-negative, we can replace this constraint using some new variable or by defining some new variable. So, let us define y1 square is equal to x1. So, since y1 square is always a non-negative quantity, that means that x1 will also be a non-negative quantity, and then we can write this problem as minimize f of y1 square x2, and now the variable is y1 and x2. So, you will see that by replacing a non-negative variable by another variable or the square of another variable y1, we have converted the given problem into an unconstrained problem, where the variable is now y1 and x2. So, in the earlier case the variable was x1 and x2. So, we retained x2 as it is, but then replaced x1 by y1 square in the objective function, and that became the unconstrained optimization problem. Now, sometimes we may want to solve the following problem, minimize f of x1 x2 subject to the constraint that x1 is greater than 0. So, now we are interested in those x1s which are strictly positive. So, here one can use a new variable. So, suppose if we define y1 such that e to the power y1 is equal to x1. So, we have defined new variable y, and we know that e to the power y1 is always a positive quantity, and therefore, in this objective function, if we replaced x1 by e to the power y1 and then treat y1 as a variable along with x2, then we have converted this problem to an unconstrained optimization problem, and we know different ways to solve unconstrained optimization problems. So, many times it may be a good idea to see whether a problem can be converted to an unconstrained problem, although there is no rule that we always have to convert an unconstrained optimization problem to a constrained optimization problem. Sometimes the constrained optimization problems are easier to solve compared to unconstrained optimization problems. Now, one can also have a problem which is of the type, say, minimize f of x1 x2 subject to the constraint that L less than or equal to x1 less than or equal to u. Now, such problems also can be converted by defining a new variable. See, for example, one can use some functions which vary over the certain range. For example, one can write x1 as so L plus u minus L sin square y1. Now, sin square y1 takes the values in the range 0 to 1. So, when sin square y1 is 0, we have x1 equal to L, and when sin square y1 equal to 1, we have x1 equal to u. So, and since sin square y1 varies in the range 0 to 1, we have x1 varying in the interval L to u, and y1 can be any real number. So, you will see that by using such transformations, the original problem can be converted to an unconstrained optimization problem. Note that these transformations are not unique, one can always come up with some new transformations depending upon the problem. Now, as I mentioned earlier that one has to be very careful when one solves this constraint optimization problems by reformulating them as unconstrained optimization problems. So, let us suppose consider a case where we want to minimize x1 plus x2 subject to the constraint x1 square plus x2 square is equal to 1. Now, let us see the problem graphically. So, we have x1 and x2 as the two axes, and the constraint set is a circle with center 0 and radius 1. And the objective function is x1 plus x2 is equal to constant. So, this is the objective function, x1 plus x2 is equal to constant. Now, we want to minimize this objective function. So, you will see that the minimum is achieved at this point. So, this point is the point. So, this is x1 star, x2 star. So, this is the point at which the minimum is achieved. So, you will see that this line, the minimum occurs at this point. And this is our solution of this problem. Now let us look at this problem and then convert it to an unconstrained optimization problem. So, we have minimize x1 plus x2 subject to x1 square plus x2 square is equal to 1. Now, if you look at the constraint x1 square plus x2 square equal to 1, what this gives us is that x2 square is equal to 1 minus x1 square, and this implies that x2 is equal to plus or minus square root of 1 minus x1 square. So, there are two possibilities. One is that x2 is square root of 1 minus x1 square, and the other possibility is the negative of the square root of 1 minus x1 square. So, suppose you choose one of these possibilities. So, let us take let x2 to be minus root of 1 minus x1 square. So, when we minimize x1, x2, so this was our earlier problem, and we use this value of x2 in this. So, we this value of x2 was derived using this constraint. So, we really now do not have to worry about the constraint. So, let us plug in this value of x2 in this, and what we get is minimize x1 minus square root of 1 minus x1 square with respect to x1. So, now you will see that this is now an unconstrained optimization problem. So, this was constraint problem, and this is now unconstrained problem. Now, we already know how to solve these unconstrained optimization problems. So, we take the derivative of this objective function, equate it to 0, and see the candidates for the local minima. Now, if we take the derivative of this objective function, what we get is that 1. So, the derivative of root of 1 minus x square is 1 over 2 root 1 minus x1 square into minus 2 x1. So, what we have is plus 2 x1, that is equal to 0, and these quantities get cancelled, and what we get is x1 to be minus square root of 1 minus x1 square, and this implies that x1 to be minus 1 over root 2, and if we substitute this value of x1 in this formula, we get x2 is equal to minus 1 over root 2. And if we look at the minimum of this objective function, so the x1 star, x2 star that we get here is minus 1 over root 2 minus 1 over root 2. Remember that this is our origin, and so the minimum lies in the third quadrant, and this is our minimum. Now, so we use this value of x2 to be minus root of 1 minus x1 square to write it as a unconstrained optimization problem and then solve it. Now, the same problem, minimize x1 plus x2 subject to x1 square plus x2 square equal to 1. Now, we use x2 to be plus square root of 1 minus x1 square, and therefore, the given problem becomes, so this was the constraint problem, and we write it as an unconstrained problem as minimize x1 plus square root of 1 minus x1 square with respect to x1. So, this becomes our unconstrained optimization problem. So, again taking the derivatives, so what we get is 1 minus x 1 by root of 1 minus x 1 square equal to 0, which implies x 1 is equal to root of 1 minus x 1 square, and this implies that x 1 is equal to 1 over root 2, and if you plug in this value of x 1 here, what we get is x 2 to be 1 over root 2. So, now let us look at this point 1 by root 2, 1 by root 2 in the earlier figure. So, you will see that this point is 1 over root 2, 1 over root 2 transpose, and this in fact is a so you will see that this in fact is a local maximum. So, when we transform the given unconstrained problem, given constraint problem to an unconstrained problem, we have to be very careful, because you saw that in this case when we took x 2 to be minus root of 1 minus x 1 square, we got the actual local minimum, and if we used x 2 to be plus root of 1 minus x 1 square and plugged in that value here, we got the local maximum. So, whenever we do any transformation of a constraint optimization problem to an unconstrained optimization problem, we have to be very careful. So, the reformulation of to an unconstrained problem is always possible, but that needs to be done with some care. The other possibility is to solve the constraint problem directly, and it is this way of solving the constraint optimization problem that we are going to concentrate upon. So, let us consider this compact way of writing the constraint optimization problem, and as in the case of unconstrained optimization problem, we are interested in deriving an iterative optimization algorithm to solve this problem, and that optimization algorithm it generates a sequence x k which converges to a local minimum. Now, one has to be very careful when one writes this, that this x k, it is always assumed that this x k always belongs to the set x. So, it is not any arbitrary sequence x k that we want to generate, but we want to generate the sequence which lies in the feasible set x. So, a typical constrained minimization algorithm is given here. The reason why I said that this is typical is that there could be some algorithms which not necessarily ensure that x k lies inside the set x, but when the algorithm converges to a local minimum, the point of convergence will be in the set x. So, those are the different types of algorithms, but the typical algorithm would look like this, where we initialize x 0 in the set x, set the iteration counter k to 0, and then while some stopping condition is not satisfied at x k, we find out x k plus 1 in x k in the set feasible set x, such that the function value decreases. Then increase the iteration counter, and the procedure is repeated till one gets a point x star, at which point the stopping condition is satisfied, and that x star is a local minimum of f x over the set x. So, you will see that in this typical algorithm or the conceptual algorithm for a constraint minimization problem, at every point or at every iteration, the point x lies in the feasible set x. So, the initial point itself is in the set X, and at every iteration you get xk plus 1 in the feasible set X, and such that the value of the function decreases. Now, there are two important points that one needs to consider here is that what is the stopping condition that needs to be satisfied at xk. In the case of unconstrained optimization problem, we said that the norm of the gradient should be less than or equal to some epsilon can be one of the stopping conditions. Now, what are the analogous conditions in the case of constrained optimization problem? Now, secondly, how do we get xk plus 1 in X, the feasible set X, such that the function value decreases? So, these are two important points that one needs to consider when one writes a constrained optimization algorithm. And in the next few lectures, we will look at what are the stopping conditions for a constrained optimization problem and how do we find the new points xk plus 1. Now, there exist different types of algorithms to solve constrained optimization problems, and depending upon the application one has to choose one of those algorithms. So, we will study those things in the next few lectures. Thank you.